Hello everyone, my name is Mikhail Terehov, and today I will be presenting our joint work with Victor Larsson on the tangent Sampson error, a fast approximate two-view reprojection error for central camera models. The problem that we're trying to solve is as follows. Given a pair of images coming from arbitrary central cameras, what is the best formulation of a reprojection error for us to use in pose refinement or in RANSAC? We could try to compute the explicit triangulation given a pair of points, but this would be too compute heavy because this would require explicit optimization with respect to the points. And so for pinhole cameras, the community traditionally solves this problem by approximating the true reprojection using the Sampson approximation. But it was only derived for pinhole cameras, and in the paper we show how to derive it for arbitrary central cameras while preserving the effectiveness of the Sampson approximation that we had in the pinhole case. Yeah. Here we present the details of the derivation. Now the true reprojection error can be written as shown on the slide. Basically, we would like to minimize the distance that we move the points on the images, but such that the moved points satisfy the epipolar constraint exactly. Now the problem is that in the epipolar constraint, we have the unprojection mapping. And typically for camera models, we only have the forward projection as an explicit formula, and the unprojection does not always have a closed form solution. And for the Sampson error, we would need to even differentiate it. Now, as we show in the paper, this problem can be solved using the inverse mapping theorem. And the Jacobian of the unprojection can be derived as a short formula from the Jacobian of the forward projection. And with this formula in hand, we can apply the Sampson approximation to our true reprojection and get the error that we call the tangent Sampson error. This formulation enjoys several nice properties. First of all, it's computationally cheap. As you can see from the formula, it's only slightly more computationally expensive than the Sampson error that you would compute in the pinhole case. Next, it improves pose estimation. As we show in the paper, it favorably compares in RANSAC and in RANSAC with other error formulation. It works for any central camera. The only thing that we require here is this mapping P, that it is differentiable, and nothing much else. Next, the error is measured in pixels, which makes it convenient for us to set thresholds, for example, in RANSAC. And finally, it doesn't require closed form unprojection function. In the paper, we compare it to 7 other error formulations. These error formulations are broadly split into 3 categories. Some measure the errors in the original image, some measure the error in the undistorted image, and some are geometric, such as, for example, the cosine similarity error. I would argue that all other error formulations suffer from one or other drawback. So, for example, the 2 other formulations in the original image are much more expensive to compute than the tangent Sampson error. Undistortion is bad because it restricts us to images with fields of view less than 180 degrees. Otherwise, we cannot undistort the image into the single pinhole frame, right? And the geometric errors are inconvenient because the thresholds that we have to set for them are not in pixels. And we compare all these error formulations in refinement and in RANSAC. So one thing that we do is we run Levenberg-Marquardt optimization with different initialization poses, and we show that the tangent Sampson error converges slightly more often than the other error formulations, especially when the initial pose in the error becomes very large. And the other thing that we do is we, of course, evaluate the errors in RANSAC. And we show that on difficult image pairs, especially the tangent Sampson error performs better than the others in terms of the median pose error, in terms of how often it converges to a reasonable solution, and it also only incurs a mild performance overhead compared to the cheapest algebraic error formulation. And finally, something that we don't go into much detail here, but in the paper we also compare the errors to the true reprojection error in terms of how closely do they approximate it, and naturally the tangent Sampson error approximates it better than the other error formulations. Thank you.